Algebraic structures, lecture 11, solvable groups. We start with a definition of a simple group. Definition: a group G is called simple provided that it is non-trivial, which means that it has more than one element, and the only normal subgroups of G are G itself and the trivial group consisting of the identity. For example, if P is a prime number, then the group ZP of all residues modulo P is simple because the only subgroups of this group are the whole group and the identity element. So it doesn't have any more subgroups, and of course these two subgroups are normal. Example 2. All other abelian groups are not simple because they have non-trivial subgroups, and these are automatically normal because the groups are abelian. Example 3. The smallest non-abelian simple group is the group A5, and this is the subgroup of S5 which consists of all even permutations on 5 elements. The group A5 has 60 elements, and one way to prove its simplicity is just to list all its subgroups and check that they all are not normal. That's a finite but a bit lengthy exercise. Next, let us talk about subnormal series. Definition: a subnormal series of a group G is a chain or a flag of subgroups which starts with the identity subgroup, we denoted by G0, then we have the subgroup G1, G2, and so on, all the way up to Gk, which is equal to G. And the condition is that each Gi-1 is normal in the next subgroup Gi, but it doesn't have to be normal in the whole group G. So it's a subnormal series. Each component of the series is supposed to be normal in the next one, but then this doesn't have to be normal in the whole group G. For example, for any non-trivial group G, the chain which consists of the identity and the group itself is a subnormal series. Example 2. Any chain of subgroups of an abelian group is a subnormal series because all components are normal already in the whole group G. Terminology: the number k here is called the length of the series, and the subquotients Gi modulo Gi-1, so they're well defined because Gi-1 is supposed to be normal in Gi, so these quotients are called the subquotients of the series. Now let us talk about refinements. Definition: a subnormal series G0, G1, G2, and so on is a refinement of a subnormal series H0, H1, H2, and so on. Both of them are subnormal series in the group G, provided that there exists R1 greater than or equal to 1, then R2 greater than R1, and so on Rm, which is greater than or equal to Rm minus 1 and less than or equal to k, such that Gri is equal to Hi for all I between 1 and m. For example, if H is a normal subgroup of G, then the subnormal series which consists of the identity, then H, and then G is a refinement of the subnormal series which consists just of the identity and of G. So a refinement has more elements than the original series. Some new subgroups are inserted between the elements of the original series. Definition: a subnormal series is called complete, or Jordan-Hölder series, or a composition series, if it doesn't have any non-trivial refinements. And the trivial refinements are the refinements when you just repeat some of the elements of the original series. For example, any subnormal series with simple quotients is complete. Again, it's a nice exercise to prove this. And now we can formulate the Jordan-Hölder theorem. Let G be a finite group with two complete subnormal series, which all consist of different subgroups. So there are no repetitions inside any of these series. Then the claim is that the lengths of these two series coincide, and there is a permutation sigma in Sk, so k is the common length, such that the corresponding subquotients in the two series are isomorphic. So the subquotient gi modulo gi minus 1 is isomorphic to h sigma of I modulo h sigma of I minus 1 for all I. The proof of this theorem is not too long, but long enough, so we refer to the literature. In particular, there are many online resources when one can read the complete proof of this theorem. Example: consider the abelian group Z6 of all residues modulo 6. It has two different composition series. The first one starts with the identity 0, then the subgroup of all elements divisible by 3, so 0 and 3, and then Z6. If we look at the subquotients, we see that the subgroup consists of two elements, so the corresponding quotient by the identity is just Z2. And now Z6 has 6 elements. If we factor out the 2-element subgroup, we get as Z3 as the subquotient. So the first subquotient is Z2 and the second one is Z3. On the other hand, Z6 has a subgroup which consists of all elements divisible by 2, so 0, 2, and 4. And now we have the composition series which starts from the identity, then goes to the subgroup 0, 2, and 4, and then Z6. And now the first subquotient is a 3-element group, so it's isomorphic to Z3, and the second subquotient is a 2-element group isomorphic to Z2. So we have two different composition series, but we see that the subquotients are the same up to permutation. So that's an illustration of Jordan-Hölder theorem. Now let us talk about solvable groups. So that's an important notion which we will use later in the course. Definition: a group G is called solvable provided that it has a subnormal series with abelian subquotients. For example, any abelian group is solvable, that's obvious from the definition. And example 2, a non-commutative simple group is not solvable. If there are no normal subgroups, we cannot construct a normal series with abelian quotients if the original group is not commutative. Here is a more interesting example: any dihedral group is solvable. Indeed, if you look at the dihedral group D2 times n, that's a group of all linear symmetries of an n-gon inscribed in the unit circle in R2. That group has an abelian subgroup which consists of all rotational symmetries. If we have an n-gon, we can rotate it by 2 pi over n and any powers of this rotation, and this generates an abelian subgroup which we denote by Rn, which consists of n different rotations of our n-gon. The index of this subgroup in the whole dihedral group is 2, so we have n rotations and 2n symmetries, and of course any subgroup of index 2 is normal. So this subgroup is normal in the whole dihedral group. The quotient has exactly 2 elements because the index is 2, so the quotient is a 2-element group, so it's an abelian group isomorphic to Z2. And the subgroup itself is abelian. Therefore, the subnormal series, which starts with the identity, then goes to the subgroup Rn, and then to D2 times n, it's a subnormal series with abelian subquotients. So this means that the dihedral group D2 times n is solvable. Now let us talk about the commutator subgroup. Let G be a group, denoted by G, G in bracket, the subgroup of G generated by all elements of the form AB, A inverse, B inverse, where A and B are elements in G. So this is usually called the commutator of A and B and denoted by A, B in brackets. Terminology: the subgroup G, G in brackets is called the commutator subgroup of G, or alternatively the derived subgroup of G. For example, the group G is commutative if and only if the derived subgroup is trivial, just consists of the identity element. And indeed, two elements commute if and only if their commutator is the identity. Example 2, if we consider the symmetric group S3, then its commutator subgroup coincides with the group A3 of all even permutations on 3 elements, and there are 3 even permutations, the identity and the 2-3 cycles. Indeed, since A and A inverse have the same parity, the commutator of any pair of elements is an even permutation. And this means that the commutator of S3 with itself belongs to A3. We know that S3 is not commutative, so the commutator, the derived subgroup, should be non-trivial. But A3 is isomorphic to Z3, and Z3, since 3 is a prime number, has only 2 subgroups, a trivial one or the whole group itself. So this implies that the derived subgroup of S3 should be equal to A3. Now let us talk about various properties of the derived group. Property 1, the derived subgroup of G is normal in G. Proof: if we take 3 elements in G, A, B, and C, and try to conjugate the commutator of AB with C, we get the following. So we get C, then AB, A inverse, B inverse, C inverse. And now we insert C inverse C between all the elements in the brackets to get CA, C inverse, CB, C inverse, CA inverse, C inverse, CB inverse, C inverse. And this is equal to the commutator of CA, C inverse, and CB, C inverse. And this implies that the conjugation of a commutator is a commutator, so which means that the commutator subgroup, what is generated by all commutators, is closed under the conjugation with any element in G, and hence is a normal subgroup. Property 2, the quotient of G by its derived subgroup is an abelian group. Indeed, if we take any elements A and B in G and write the commutator of their classes in the quotient, then of course by definition this is the class of the commutator of AB. But since the commutator of AB belongs to the derived group, we will just get the derived subgroup. And this means that any pair of elements gives us the classes which commute in the quotient. And this implies our statement. And property 3, if H is a normal subgroup of G, such that G modulo H is abelian, then H contains the derived subgroup. In other words, the derived subgroup of G is a minimal, with respect to inclusions, normal subgroup of G, such that the quotient modulo it is an abelian group. Proof: if A and B are 2 elements in G, then let us write down the condition that they commute in the quotient. So if we commute the classes of AH and BH, we by definition will get the class of the commutator of A and B. And since G modulo H is abelian, this means that the commutator of A and B should belong to H. But then A and B were arbitrary, this means that all commutators belong to H, so H contains the subgroup which is generated by those commutators. And this establishes our property 3. Now we can talk about the derived series. Let G be a group, set G upper 0 to be the group G. And now define G upper I for all positive integers I recursively as a derived subgroup of G upper I minus 1. Then we have a descending chain of subgroups. So G0, which is G, has a normal subgroup which is G upper 1. This has a normal subgroup G upper 2, and so on. And this is a subnormal series. Well, formally, it doesn't have to go all the way to the identity, so we can add the identity as a starting point if we wish. And this series is called the derived series of G. Let us note that each G upper I is normal in G upper I minus 1, but it doesn't have to be normal in G. So it's really a subnormal series, not a normal series. So for example, if G is abelian, then the derived series is trivial. So G upper 1 is the identity subgroup, and that's it. Example 2, the derived series of S3 consists of, it starts with S3, the derived subgroup is A3, but A3 is abelian, so its derived is the identity. So we have 3 elements in the derived series. Now we can use this to formulate a solvability criterion, theorem. A finite group G is solvable if and only if there is K greater than or equal to 0, such that the case-derived subgroup G is trivial, is equal to the identity group. Proof. Assume that G upper K is trivial for some K. Then we can look at the derived series, and this is a subnormal series with abelian subquotients, because each component is normal in the previous one, and the quotient is abelian. The quotient by the derived subgroup is always abelian, and that's a definition of being solvable. Conversely, assume that our group G is solvable and take some subnormal series with abelian subquotients. Then, in particular, the quotient of G modulo G k minus 1 is abelian. But then, by one of our properties of the derived subgroups, it means that gk minus 1 contains the first derived of G. And exactly the same argument by induction tells us that the subgroup gk minus I of this series contains the i's derived of G. But then, in particular, the case derived of G will be a subgroup of G0, which is a trivial subgroup. And this gives exactly the claim of the theorem. Now let us discuss subgroups and quotients of solvable groups. Proposition: any subgroup and any quotient of a solvable group is solvable. Proof: if H is a subgroup of G, then the i's derived of H is a subgroup of the i's derived of G by definition, for any I. So if G is solvable, then some G upper K is 0, which means that the corresponding H upper K is 0, and this means that H is solvable by the previous criterion. For the quotients, let K be a normal subgroup of G, and consider the quotient Q of G modulo K with a natural projection pi from G onto Q. Then, the first derived of Q is generated by the classes of the form the commutator of AB times K, where A and B are elements in G. And this means exactly that the first derived of Q is the image of the first derived of G under the map pi. And similarly, by induction, the i's derived of Q is the image of the i's derived of G under the map pi. So if G is solvable, then some G upper K is equal to 0, and then this means that the corresponding Q upper K is also equal to 0, and so Q is solvable by the previous criterion. Finally, let us talk about extensions. Proposition: let G be a group and H a normal subgroup of G. If both H and G modulo H are solvable, then so is G. Proof: since we assume that G modulo H is solvable, the case derived of G modulo H is trivial for some fixed K. And this means exactly that the case derived of G belongs to H, because we take the quotient modulo H for this number K. Next, since H is solvable, some derived subgroup of H is trivial. So let's say the m's derived of H is trivial. But this implies that the m's derived of the k's derived of G, which is exactly the k plus m's derived of G, is trivial. And so again, G is solvable by our criterion. We can use this to obtain the following result about the P groups. So let P be a prime number. Recall that a P group is a group whose cardinality is a power of a prime. So it's a power of this P, some power P to the power K. Theorem. Any P group is solvable. In order to prove this theorem, we will use the following lemma, which we will prove on the next slide. Any non-trivial P group has a non-trivial center. So now how to prove the theorem using this lemma? We do induction on the cardinality of G. By our lemma, G has a non-trivial center. So assume that G is non-trivial, then it has a non-trivial center. The center is solvable because it's abelian. It's a normal subgroup of G, and since it's a non-trivial center, the quotient of G modulo the center has less elements than G. So it is solvable by induction, because we do induction on the cardinality of G. And so by our previous proposition about extensions, it follows that G is solvable. So all what we need is to prove this lemma. So let's prove the lemma. So let G be a non-trivial P group. Then, of course, as any group, G is a disjoint union of conjugacy classes. The conjugacy classes are orbits with respect to the conjugation action of G on itself, and the cardinality of each orbit must divide the order of the group. So the cardinality of each conjugacy class divide the order of the group, and hence is a power of P. There is at least one singleton conjugacy class, namely the conjugacy class of the identity. But the sum of the cardinalities of all conjugacy classes must be a power of P, so it's divisible by P. So it means that the number of singleton conjugacy classes must be divisible by P as well, because all non-singleton conjugacy classes have cardinalities which are divisible by P. And it remains to note that the center is exactly the union of all singleton conjugacy classes. An element is in the center if and only if it commutes with all other elements, which means that if and only if you conjugate it by any other element, you stay at this element. Let's do one example. Consider the octonian group O. That's a group with 8 elements, plus minus 1, plus minus I, plus minus j, plus minus k, where minus 1 squared is equal to 1, as usual, and the rest of multiplication is given as follows. I squared, j squared, and k squared are all equal to minus 1, and ij is equal to k, jk is equal to I, and ki is equal to j. Note that here in particular, if you multiply j and I, so this means the same as multiplying j with jk, j squared is minus 1, so it gives us minus k. So ij is equal to k, ji is equal to minus k, so I and j do not commute. And then by symmetry, I and k do not commute, and j and k do not commute. So this group has 8 elements, so it's 2 to the power 3, so it's a 2 group. And it's easy to see that the non-trivial center of this group consists of the identity and of minus 1, so by definition minus 1 is central. If we take the quotient of O modulo the center, we get a group with 4 elements. So these 4 elements are the classes of 1, I, j, and k. And now if we square any of them, we get minus 1, which in this quotient is equal to 1. So all non-identity elements in this quotient have order 2. So the quotient of O modulo the center is z2 times z2. So we have here a subnormal series which starts with the identity, goes to the center is 2 elements, so that's z2. And then we go from the center to the whole group, and the quotient is z2 times z2. It's an abelian group, so we have a subnormal series with abelian subquotients. So O is a solvable group. Now some very general results, which we will not go into detail, about other known cases of solvable groups. A theorem due to Burnside from 1904, any group of order p to the power a times q to the power b, where p and q are prime numbers, is solvable. So not only P groups are solvable, but groups whose orders only have two prime divisors, they all are solvable. And here is a very famous result, which is called Fate-Thompson theorem from 1962-63. All groups of odd order are solvable. So this is a really fundamental and very difficult foundational result in the theory of finite groups. One corollary of these two statements is that all simple finite non-abelian groups have even order. Moreover, this order has at least three different prime divisors. So in some sense, solvable groups are the opposites of the simple groups. So therefore, we talked a bit about simple groups in order to have this parallel, the solvable groups, in this lecture. And now some spoilers for the second part of the course. The terminology solvable group comes from the applications of such groups in Galois theory. In the second half of the course, we will look at fields and their extensions. Each field extension will give rise to a certain group, which is called the Galois group of that extension. And then the solvability of polynomial equations in radicals turns out to correspond precisely to the solvability of the Galois group of the field extension, where we start from the rational numbers and add to it the coefficients of the polynomial which we consider. Also, ruler and compass constructions in the plane can be studied in a rigorous way using certain properties of the Galois groups. So it turns out what you can construct using ruler and compass can be described using the properties of the corresponding Galois group. It not only that should be solvable, but the subquotients in the subnormal series should be very, very specific. Okay, some additional problems and questions at the end. Problem question 1. Prove that A phi is a simple group. Problem question 2. Prove with all details that a subnormal series is complete if and only if all its subquotients are simple. Problem question 3. Let G0, G1, and so on Gk be a subnormal series of a finite group G. Show that the cardinality of G equals the product of the cardinalities of the subquotients of this series. Problem question 4. Prove with all details that any subgroup of index 2 is normal. And problem question 5. Prove that the group S4 is solvable. Thank you very much and see you next time.